The periodic table tells you about specific trends within groups, and the way that it does that is by actually letting you know the number of valence electrons each group possesses. So if you look at group 1 right here, this entire group, all of these atoms have one valence electron. So for example, for lithium, it has a 1s2, 2s1 electron configuration. So it has one valence electron, which is one outermost electron, which is in that 2s orbital. So this group right here has one valence electron. Group 2 has two valence electrons. Boron, that has 3, 4, 5, 6, 7, and then 8. Because remember, your noble gases have that perfect octet, 8 valence electrons, which is the goal, which is the most stable configuration. Now, if you look here, if I have one valence electron, lithium wants the electron configuration of helium. Okay? And in order to do that, it either can lose one valence electron or gain 7. So it's going to lose one valence electron because that's easier than gaining 7. So its charge is going to be positive 1. For group 2, they're going to lose 2 valence electrons, so it's going to be positive 2. Group 3, lose 3 valence electrons. Now, once I hit group 5 here, it's easier to gain 3 electrons to assume the electron configuration of a noble gas than to lose 5 valence electrons. So the charge of group 5 is going to be negative 3. Group 6 is going to be negative 2. They're going to gain 2 electrons in group 7, negative 1. So the charge here is extremely important as we prepare to write the formula for ionic compounds, because when we're writing the formulas of ionic compounds, we need to know the charge of the metal and the non-metal that are involved. So notice how nice the periodic table is in the sense that it lets us predict what the charge is going to be simply based on the location of the atoms. In this section, we're going to look at how those ions and the charges that we can now predict contribute to the formation of ionic compounds. This should be a quick review for you. I'm just going to read through this to make sure we're on the same page. Atoms can readily lose or gain electrons to become ions, and we've looked at characteristics such as ionization energy and electron affinity in order to understand which atoms accept and which lose. So specifically, those ions with positive charge, they lost electrons. They are called cations, while negatively charged ions are called anions. Now, metals tend to lose electrons, and the reason why they do is because they have a very low ionization energy. So it's very easy to remove electrons in order to form cations, while nonmetals tend to gain electrons, and the reason why they do is because they have a very high electron affinity. They attract electrons to themselves, while metals easily lose them. The chemical properties of ions are extremely different than their atoms. So for example, sodium chloride, NaCl, sodium ion, which has a +1 charge, that is very different chemically from regular atomic sodium. Sodium in its atom form is extremely reactive with water and will actually blow up. So if the chemical properties between atoms and ions were actually the same, every time you ate salt, there would be an explosion. So thankfully, the chemical properties between ions and atoms are very different. Now, I'm going to be talking about ionic compounds, how to name them, how to write their formulas. You've been working with them quite a bit already. Now you're actually going to learn how to apply what you've learned. So, ionic compounds occur when electrons are transferred, okay, and there will therefore be a positive and a negatively charged ion involved. The positively charged ion and the negatively charged is an ionic compound. And so you can see here, here's your lattice structure right here, your crystal lattice. The fact that sodium has a positive charge, chlorine has a negative charge, and in order to maximize their attraction, they create this lattice structure that maximizes attraction. That should all be reviewed though. Let's talk about actually writing the formula based on the name of the ionic compounds. Ionic compounds have to be neutrally charged, and this is going to be vital in understanding how to write the formula for the ionic compound. Now keep in mind, the formula for an ionic compound is actually the empirical formula. It's the simplest whole number ratio of atoms because that's how they form. Because they don't actually exist as molecules, instead you have ions that are attracted to each other in this lattice structure. So Let's look at magnesium nitride. Magnesium has a +2 charge. Nitrogen has a -3 charge. Okay? Nitride is nitrogen, the anion of nitrogen. So if magnesium has a +2 charge and nitrogen has a -3 charge, your formula for your ionic compound will be Mg3N2. All right? Now, when we're working with ionic compounds, we aren't always dealing with ions that are monatomic, meaning just one atom. Instead, we can also have polyatomic ions. And here's a list of polyatomic ions. You need to memorize these for the AP and for the rest of the class from now on. I'm assuming that you have these memorized. What you'll notice is that there are a lot of trends. So for example, if you look at NO2 negative, that's nitrite, while NO3 with a negative charge is nitrate. So the difference between an ite and an ate is simply one oxygen. So you'll see a lot of patterns, so there won't be that much memorization that's needed. But if I say, for example, that I have I don't know, sodium sulfate, you should know that the chemical formula for that is Na2SO4. Right? That's basic knowledge that if you didn't acquire that in regular chemistry, you need to acquire that now and sit down. I would recommend making flashcards if you need to for these, but at this point you now know your polyatomic ions. You've learned how to write the formula for ionic compounds, and now you're going to learn how to name ionic compounds. Now there are two different types of ionic compounds that I can be dealing with. The first one is of metals with known charge. Now, this includes your group 1 alkali metals, your group 2 alkaline earth metals, and then group 3 with aluminum having a +3 charge. If I know the charge of my metal, all I need to do is write the name of my metal, followed by the name of my nonmetal, and it's going to have an IDE ending. So for example, fluorine, I would get rid of the INE ending and I would make it IDE. So it would be fluoride. Oxygen becomes oxide, chlorine becomes chloride, etc., etc. Now, for the second group, second type of ionic compounds, you would have metals of unknown charge. So for example, if you look at the example problem that I gave you MnS. Manganese is a transition metal. I don't know the charge of manganese. It can vary. Okay? And therefore, I need to figure out what the charge is and include it in the name. Just to go back really quickly, for this first type, it includes your group 1, group 2, group 3 metals, because you know the charge, and then it also includes your two exceptions. Keep in mind, silver has a +1 charge, and zinc has a +2 charge. So since manganese is not an exception, I don't know the charge just looking at the periodic table, and therefore I need to include it in the name. And here's why. If I were to just write the name of manganese and sulfur together, based on what I did up above, it would be manganese sulfide. Now, here's the issue. I don't know the charge of manganese. And if I were to just give someone manganese sulfide, they wouldn't know what the charge of manganese would be, and therefore they would not know the formula for this ionic compound. And so as a result, I have to figure out the charge of manganese in this compound, and I have to somehow write it in the name to let the person involved know what the charge of manganese is. Well, sulfur has a -2 charge, and since ionic compounds are neutral, that means manganese must have a +2 charge. So the way that I write this, it would be manganese, and I would put the charge of manganese in parentheses. So it would be manganese 2 sulfide. So I use Roman numerals to represent the charge. Notice this is not telling you how many manganese you have, instead it's simply telling you what the charge of manganese would be. I've looked at ionic compounds that simply have a monatomic cation and an anion. What if I have a polyatomic anion? So for example, if I gave you, as an example, Na3 PO4. Now, PO4 is a polyatomic ion, it's phosphate, and so all you have to do, you just follow the same rules as what we did before, except instead of writing an IDE ending, you just write the name of the polyatomic ion. So here, sodium, Na, I know the charge of sodium always, it's +1, so I don't have to include the charge in the name, so it would be sodium phosphate. And that's all there is to it. All right, now we're going to leave ionic compounds and we're going to go to molecular compounds. Remember, molecular compounds are created by nonmetals, all right? And the bond that attracts those atoms are covalent bonds. Now, we have two different terms that we have to talk about and review, which we talked about at the beginning of this class, molecular formulas and empirical formulas. Remember, for ionic compounds, they are always the empirical formula, the simplest whole number ratio of atoms. However, for molecular compounds, since they do exist as molecules, we have to distinguish between molecular formulas and empirical formulas. Molecular formulas are the actual numbers of atoms in a molecule, okay? While an empirical formula is the relative number in atoms. So for example, if I have hydrogen peroxide, which is H2O2, H2O2 is the molecular formula for hydrogen peroxide. The empirical would just be HO, since that would be the simplest whole number ratio of atoms. When we're naming molecular compounds, it's different than when we are naming ionic compounds. And the reason why is because we are not dealing with charges when we're talking about molecular compounds. There isn't an uncrossing charges figuring out whether or not I need to put the Roman numerals for the charge of the metal or not, because both nonmetals have negative charges in their ionic form. Therefore, we need to use prefixes. The prefixes are here. You do need to memorize these, but with a little bit of practice, you will get them really quickly. Now, for P3F4, I know I have 3 phosphoruses and 4 fluorines. So therefore, the name of this molecular compound is triphosphorus tetrafluoride. Okay, because I have 4 fluorides and 3 phosphoruses. Notice I keep the IDE ending for the second ion, okay, triphosphorus tetrafluoride, and we're good to go. Now, let's talk about actually writing the formula based on the name. If I give you nitrogen trichloride, notice one thing that is actually a rule when I'm naming molecular compounds. Notice for nitrogen, there is not a prefix. Notice that the prefix for mono is 1. So when you are writing the name of a molecular compound, you never start off, if your first atom, there's only one of them, you never start off with mono. So instead of saying mono nitrogen trichloride, by saying nitrogen trichloride, it's implied I only have one nitrogen. Is it wrong if you write mono in front? Yes. Don't write it. We don't say mono nitrogen trichloride. So the formula for this is going to be NCl3. Okay? The last thing that we have to talk about is naming acids. And the reason why I left this for right now is because it allows you to apply what you learned with naming ionic compounds to naming acids, so you can review. Keep in mind, just as a review, an acid is a compound that begins with hydrogen. Now, water and H2O2 are not acids. For right now, they're not acids. So if you see a compound starting with hydrogen, assume that's an acid unless you're talking about water or hydrogen peroxide. So if you have an acid that has an anion whose name ends in IDE, all you need to do is change that IDE to ic and add the prefix hydro to the name. So if you look at this example, I have HBr. Br would be bromide, so I would change that to bromic and put hydro in front. And so the name of this acid is hydrobromic acid. If instead I have a polyatomic ion instead of just a monatomic anion, then if it has an ATE ending, I change that ATE to ic. If it has an ITE ending, I change that to us. Notice I don't have hydro in front. So if I have HNO3, NO3 is nitrate, polyatomic ion nitrate. Therefore, the name of this acid would be nitric acid. For HNO2, because that's nitrite, it would be nitrous acid.